Let's find the inverse Laplace transform of this function, s squared minus 3 over s cubed minus 1. This technique, the form of the Laplace transform suggests using partial fractions. The degree of the numerator is less than the degree of the denominator. And so to get started, we just need to factor the bottom. Now the bottom, s cubed minus 1, is actually the difference of two cubes. And so you might have memorized from a previous class the formula for the difference of two cubes. If not, then this can be found by using synthetic division. So the possible rational roots of the bottom, s cubed minus 1, are going to be plus or minus 1, things that go into the constant term, negative 1, divided by things that go into the leading coefficient, which is also 1, so plus or minus 1. And clearly 1 is a root. So if you plug in 1, you get 0. So clearly 1 is a root. The question is, what is the quotient after you divide out, after you factor out that part? So we get 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 1 plus 1 is 0. So this tells us that s cubed minus 1 is equal to s minus 1 times s squared plus s plus 1. 1s squared plus 1s plus 1. Okay, so let's now take a look at the fraction s cubed minus 3 over s cubed minus 1. This is going to be equal to s squared minus 3 over s squared plus s plus 1, s minus 1. So this breaks up into two parts, as plus b over s squared plus s plus 1. S squared plus s plus 1 does not have any real roots. This has complex roots. So that's an irreducible quadratic. My rule for irreducible quadratics is that I have a linear term on top plus c over s minus 1. Once again, I have a cubic on the bottom, and so not surprisingly, I have three things that I have to solve for up here. Okay, now clear out the denominator. We get as plus b times s minus 1 plus c times s squared plus s plus 1. Okay, to solve for a, b, and c, the first thing I'm going to do is just figure out what c is. Let's let s equal 1. On the left-hand side, I get negative 2. If I let s equal 1, then this part is 0. If s equals 1, then I get 3c over here. And therefore, that c is equal to negative 2/3. So I can figure out one of these pretty simply that corresponds to the linear term. Now, unfortunately, to figure out a and b, there's really no simpler way than just simply multiplying out. So let's go back to the top equation here, and let's multiply out. We get that s squared minus 3 is equal to as squared minus as plus bs minus 1, or minus 1b, plus cs squared plus cs plus c. Okay, now if I match the coefficients, I get 1 is equal to a, then I've got a plus c over here. I've got 0s over here. And on this side, if I take the s terms, I get negative a plus b plus c. And then the constant terms, I get negative 3. Constant terms over here, I get negative b plus c. Now that looks like a system of three equations and three unknowns, and that's because it is a system of three equations and three unknowns. But the good news is that I've already solved for c, and so the work that I have to do is going to be a whole lot less. C is equal to negative 2/3, so that means that 1 is equal to a minus 2/3, and therefore a is equal to 5/3. Using the bottom equation, we get that negative 3 is equal to negative b minus 2/3. And so solving for b, we get b is equal to 7/3. And so that means that s squared minus 3 over s squared plus s plus 1 times s minus 1 is going to be equal to 5/3 times s plus 7/3 over s squared plus s plus 1. Then I have minus 2/3 over s minus 1. Okay, so that's partial fractions. Now let's talk about what we're going to have to do to use the differential equations part of the course. This first fraction here, 2/3 over s minus 1, that's going to fit this pattern, 1 over s minus 1. So I know how to take the inverse Laplace transform of this. This part requires a little bit more thought. If I go down into my table here, I don't have anything that looks like this, s squared plus s plus 1, but I do have things where I've partially completed the square. So I see s minus a squared plus b squared. So to figure out the inverse Laplace transform of this, what I need to do is complete the square on the bottom. So to start that, I get 5/3 s plus 7/3 over s squared plus s plus a fourth plus 3/4 minus 2/3 over s minus 1. So I have a fourth here because I have 1 here. 1 divided by 2 is a half, squared is a fourth. And so I get 5/3 s plus 7/3 over s plus 1/2 squared plus 3/4. And to match what I have in the table, I'm going to write this as square root of 3 over 2 squared minus 2/3 over s minus 1. Okay, so we're making good headway now. Okay, let's go back to the table and see how this fits what's in the table. Let me try to slide this underneath. There we go. Okay, so this comes pretty close to fitting the forms that I see here. So constant over s minus a plus b squared. This almost fits, but notice that here I have s plus a half. So I need to have an s plus a half up here so that I can use this formula in the table. So I have s here, but I need to get s plus a half altogether. So to make that happen, I'll just simply force it. So this is equal to 5/3. Let's force the s plus a half in. Then, of course, I have to subtract to compensate 5/3 times a half plus 7/3 over s plus a half squared plus square root of 3 over 2 squared. Then the second fraction just comes along for the ride, minus 2/3 over s minus 1. And so we get 5/3 s plus a half over s plus 1/2 squared plus square root of 3 over 2 squared. This remaining part is going to be 7/3 minus 5/6. So just do the arithmetic over here on the side. 7/3 minus 5/6 is 14/6 minus 5/6, or 9/6, or 3/2. So 3/2 over s plus 1/2 squared plus square root of 3 over 2 squared minus 2/3 over s minus 1. Okay, we're almost home, except for one small catch. So let's again take a look at the table. So here's where we are right now in the calculation. This part matches this formula perfectly. However, for this part to match, I need to have a b on top. So there's b squared. So I need to have a square root of 3 over 2 on top here to match the formula. So let me write this as, so 5/3 s plus 1/2 s plus 1/2 squared plus square root of 3 over 2 squared. Again, let me force a square root of 3 over 2. S plus 1/2 squared plus square root of 3 over 2 squared. What's left is going to be square root of 3. So square root of 3 times square root of 3 is 3. then minus 2/3 over s minus 1. I've now written this in a form that exactly matches what I see on screen here. So the first part here, s minus a over s minus a squared, that's this part. So the inverse Laplace transform of s squared minus 3 over s cubed minus 1. This first part is going to be 5/3. Now let's take a look at the formula. E to the minus at cosine bt. So I have my a is negative 1/2. My b is square root of 3 over 2. So we'll have e to the minus t over 2 times the cosine of t times square root of 3 over 2. And that's the inverse Laplace transform of this. Plus, I've got an extra square root of 3 on the side here. Then using this formula, we have b over s minus a squared plus b squared. So this part, ignoring the square root of 3, exactly matches this. Again, a is going to be negative 1/2, b is square root of 3 over 2. So I have e to the minus t over 2 times the sine of t square root of 3 over 2. And then lastly, let's come back to near the top of the table, minus 2/3 over s minus 1, that matches this. So I have minus 2/3 times e to the t. And so after this long calculation, that is the inverse Laplace transform of that rational function.